Okay, welcome to the second second block of the comps 2019 symposium for geology. I realized that I didn't thank my advisor or my family, so thanks. Dan, you were super helpful, volunteer, awesome. Now I'd like to introduce my freshman year roommate, Matt Carter, with his comps, developing an inverse model of the fossil ridge transform intersection in the Troodos ophiolite in Cyprus. Sure.
So I'm going to be talking about combining dike data from the Troodos ophiolite in Cyprus along with statistics and a dynamic model to create an inverse model for a fossil ridge transform intersection. And so this is a picture of a sheeted dike complex with a bunch of dikes here and Josh Davis. So the main things that I want you to take away from this talk are that I developed a model to predict the half spreading rate and slip rate for the Troodos ophiolite ridge transform system. My approach combined a dynamic model and statistics to develop an inverse model. And the general method is promising, but the results are dubious. So what is a ridge transform intersection and why do we want to model it? So a ridge transform intersection is a very common feature along mid-ocean ridges, and it occurs when you have two ridge segments that are offset from each other, which forms a transform fault in between them. And so some interesting features about them is that the ridge locally curves towards the transform fault, as you can see here and here. And also other extensionary features also show this curving, especially in the inside corner where the stresses are greatest because it has the stresses of both the ridge and transform acting on it. And then there have been multiple attempts to model a ridge transform intersection. This is one particular model from Fitzmorgan from NPA. And you can see it has the same basic structure with the ridge here and the transform fault here. And this model was created by, was a numerical model that you apply forces to the ridge and transform to try to get stresses similar to that of a ridge transform intersection. And we do see that the maximum stress direction, which should be parallel to these extensional features, do show the same curve towards the ridge, towards the transform fault that we see in actual ridge transform intersections. However, this model didn't actually use any real data. What they did was they just produced conditions that they think are similar to what a ridge transform should look like to try to produce results to learn more. And so primarily all the models of ridge transform intersections have been forward models and that apply conditions and try to get what the stresses would look like in a actual ridge transform intersection. And none of these use real data. And so we wanted to try to use real data in our analysis, but it's hard to get data of ridge transform intersections since they're on the bottom of the ocean. And so that's where we use an ophiolite. And so the Troodos ophiolite, this is a map of the Troodos ophiolite in Cyprus. And we see that an ophiolite is a section of oceanic lithosphere that has been placed on continental crust so that we can access it on land. And so we see that the Troodos ophiolite has a full suite of oceanic lithosphere rocks from ultramafic mantle rocks to basalts. And it also has two interesting features, the Sylvia Graben and the Arakapis fault, which are thought to be a fossil ridge and a fossil transform, which makes the whole ophiolite a fossil ridge transform intersection that we can study to see what the conditions were in the past, like the conditions of this ridge transform were in the past. And so we need a data set to look at, and so the data set that we're looking at is dike data, and here is all of the collected dike data that I did not collect, but Sarah Titus and colleagues collected all of these points. And so we want to try to create an inverse model using this dike data to see if we can model this ridge transform intersection. And so what we want from the model is we want a model that we can validate with the dike data. And so the way we do this is by predicting the data that we have and comparing the predictions to the data that we've observed. And so we want to create a model that is able to predict dipole data. And so the first step we need is we need to figure out where the dikes formed in their initial forming location. And so the way we do this is we have our model predict the velocity field, and then we can trace back the dikes through the velocity field to their initial forming location. From here, we want to know where the what the dipole direction is, and the dipole is the vector tangent to the dike plane. We want to know what that direction is. So to think about that, we can first think about how dikes actually form. And so here's a picture of some sheeted dikes, and here's the dike outline. And so dikes form as there is opening in a rock, and that opening fills with magma. And so the way we can think about this is that the direction of opening is perpendicular to the plane of the dike. And so, in other words, the least compressive stress is going to be perpendicular to the dike plane. And so, if our model can also predict these stress fields, we can also get an initial dipole direction based on the least compressive stress direction. After that, we can bring the dike back through the trajectory that we brought it to its initial location from, and we can use what's called the deformation gradient tensor to figure out how much rotation there is along that path. And that deformation gradient tensor is calculated using the velocity field. And so then we would have our predicted dipole and our observed dipole, and we can compare them using the angle between them. And the goal is to get this angle as small as possible. And so what we need from a model in order to incorporate this dike data into the model is we need a velocity field and a stress tensor field. And so how do we, and so if we can get this, we can predict the dikes, and then we can compare different models based on their ability to predict the dipole orientation. And so how do we get this velocity and stress fields? So this is what's known as a finite element mesh, and I don't have too much time to explain much about it, but this would be where one ridge is, this would be another ridge, and then this would be the transform. And what we did is we applied displacement boundary conditions to the north and south of this model that are relative to this half spreading rate, and displacement boundary condition on the transform faults that is relative to the slip rate. And then we also defined some linear elastic material properties based on a temperature model. And so the overall structure of this model is that we choose parameters such as the half spreading rate and the slip rate. We use those parameters to write what are known as pilot files, which is the partial differential equation solver that gets us the velocity and stress tensor fields. We run pilot to get the velocity and stress tensor fields. We use that with the data to compute the trajectories of each station. We compute the finite deformation tensors from the velocity field, and then we use those together to predict data. Finally, we compare the predictions to the field data to get a likelihood, which is how likely that the parameters fit the data that we have. Then we run it over again, changing the parameters a bit, and we run this over and over and over again until we find the maximum likelihood. And this is called a maximum likelihood estimate. So here are our results. So on the right is a contour plot of half spreading rate and slip rate with the log likelihood plotted in the colors, and darker colors are a better log likelihood. And so we can see that the best rates are with low slip rates and high spreading rates. And this already you can already tell that this is a little bit wonky, because the highest rate actually has a negative slip rate, which corresponds to a left lateral slip rate, which is not true. And then for our, this was created using 30,000 likelihoods from an analysis that was run on the CMC servers for about 5 to 10 weeks. I can't remember exactly. And so this was run with only 23 dikes because otherwise it would take too long. We also were able to run one maximum likelihood estimate with all 2,298 of the dikes. And that took about two and a half weeks to run. And with that result, we got a half spreading rate of 101.2 millimeters per year, a slip rate of 10.3 millimeters per year, the Young's modulus linear coefficient of 0.52, and thermal diffusivity of 68.6. And if you know much about mid-ocean ridges, that's a little, the half spreading rate is very quick, much quicker than you would expect, and the slip rate we would like to think would be close to the half spreading rate instead of very much lower. And so what's another way we can look at these results to see how good they are? So we can also look at the actual dipoles plotted on the stereo net. The stereo net, just for a little background, the points that are closer to the edge are more vertical dikes, the points that are closer to the center are more horizontal dikes. We also, the easting is plotted in color, and so red is closer to the ridge and blue is further from the ridge. And so we do see that there is some pattern between these. There is a little bit of rotation that you can notice as you get further from the ridge. And if you look at the predictions, they are a lot closer to the edge. They're a lot more vertical. You don't see the same horizontal, we don't see the same subvertical dikes that we see in the other. We do still see some rotation, but it is not as strong. And so we can also look at a histogram of this and see that the average angle between the dipole and the observed pole, the predicted dipole and the observed dipole, is about like 48 degrees off, when the maximum is 90. And so there are a couple reasons why this could be like this. So I'm going to just list a couple shortcomings of the model. So the boundary conditions are all applied in the horizontal plane, which could lead to less three-dimensional results. Also, we assume that dikes were perpendicular to the least compressive stress, which is not necessarily the case. And then there's a couple of others. The depth estimates of dikes were just estimates. The design of pilot is not conducive to this type of analysis. And also there's some human error. So back to the main takeaways. I developed a model to predict the half spreading rate and slip rate of for the Trotus ophiolite ridge transform system. This approach coupled dynamic model and statistics to develop an inverse model, and the general method is promising, but the results are dubious. I would like to thank Sarah Titus and Josh Davis for advising me through this process, and Sam Bacon for providing some of the code and foundational work that I use, and then also NSF for the grant that allowed me to do this research. Any questions? So the map. All the way back. So this map. So yeah, it's like here and here. Very conveniently oriented the same way as all the models, with the ridge going north and the north-south and the transforming east-west. Yeah?
How well do you know the temperature?
So I did, a whole other part of my project was developing a temperature model, which I do have a little extra slide for. Let's just go through all of this. So here is my temperature model. So I used this equation up here for the temperature gradient, and here are just two temperature gradients there, and then I used that with this equation to get Young's modulus based off of the temperature gradient. It was a pretty rough estimate, and then I also, there's other applications with the temperature between across the transform, because there's a whole other slew of models trying to figure out temperature gradients at a ridge transform intersection, because you have to think about how much temperature is crossing that transform boundary. But I didn't go too far in depth in that, but that's the equations that I used.
What was the actual data collected? Was it like paleomag or like a depth?
The actual data is dipole oriented directions, so just measurements of the directions of things.
Okay.
All right, you better move on. Thank you.